This video discusses pericyclic reactions, which are reactions that occur through a cyclic transition state without ionic or free radical intermediates. And there are three main types. The first is the cycloaddition reaction. In this reaction, you're forming a ring, and you're forming two new sigma bonds and breaking two pi bonds. So here are the two new sigma bonds that you formed, and you lost two of the three pi bonds. The second type is an electrocyclic reaction. In this reaction, you're going to have a reorganization of pi bonds with the loss of one of the pi bonds and a creation of the new sigma bond here. And the final reaction is the sigmatropic rearrangement. In this, you are maintaining the same number of double bonds, but everything is being reorganized. And this sigma bond will break, and you have a new sigma bond forming. There are four characteristics of pericyclic reactions. The first is that the mechanism is concerted. It happens all in one step without intermediates. The second characteristic is that the mechanism involves a ring of electrons moving around in a closed loop. Third, the transition state is cyclic. And four, the polarity of the solvent generally has no effect on the reaction rate. The difference between these three types of pericyclic reactions is in the change in the number of sigma bonds and pi bonds. So for the cycloaddition, we're forming two new sigma bonds and losing two pi bonds. In the electrocyclic reaction, we are gaining a sigma bond and losing one pi bond. And in the sigmatropic rearrangement, we are not having any change in the number of sigma or pi bonds, but their placement will change. Of these three reactions, I will focus the most on the cycloaddition, and in particular, a type of cycloaddition called the Diels Alder reaction, named after the chemist who discovered it. This is a type of 4+2 cycloaddition. 4 because 4 atoms are involved with one of the reaction partners, and 2 atoms are involved from the other reaction partner. In this reaction, you have a pi bond forming a new sigma bond, a second pi bond moving over, and then the third pi bond forming the second sigma bond. So here in red, you see the new sigma bonds formed, and you're going to use 3 curved arrows as shown here to indicate the mechanism. Most Diels Alder reactions are thermodynamically favored at low and moderate temperatures, and that's because the product stability dominates. So you form 2 new sigma bonds, which are stronger than pi bonds. So that is a thermodynamically favorable process when it comes to enthalpy. However, at high temperatures, the retro Diels Alder can predominate, and that's because entropy becomes the dominant factor there. So you're going from 1 molecule to 2 molecules, which is entropically favored. So think back to the delta G equals delta H minus T delta S Gibbs free energy equation. So the temperature will affect the entropy term. So the pi bond to sigma bond conversion provides a negative delta H. So that is enthalpically favored because those sigma bonds are stronger than the pi bonds. However, it's entropically disfavored because you're going from 2 freewheeling molecules to 1 more organized, rigid molecule. So whenever you go from more molecules to fewer molecules, that's entropically disfavored. For any reaction to be spontaneous, you need the delta G to be overall negative. So for Diels Alder, the enthalpy term is going to be negative, and it must be larger than the entropy term, which will be positive. So what will happen is at very high temperatures, the entropy term begins to dominate over the enthalpy term, and that's why we get a retro Diels Alder. And therefore, if you want to do a Diels Alder reaction, you want to keep your temperature below around 200 degrees. We give names to the 2 reactants in the Diels Alder. One is the diene, and this is a conjugated diene. And then the other reaction partner is the dienophile, phile meaning loving. So this is something that loves to react with a diene. Now typically a dienophile really needs an electron withdrawing group. So X needs to be electron withdrawing. Or the reaction will require high temperatures, which as just explained doesn't favor product formation because you start favoring the reverse reaction too much due to that entropy factor. So these would be examples of good dienophiles. The groups highlighted in red are electron withdrawing. And one way to think about this is you know that the carbonyl has a delta plus on the carbon and a delta minus on the oxygen because that oxygen's more electronegative, so it pulls electron density away from that carbon. And now since the atom connected to this alkene is partially positive, it's going to have an electron withdrawing effect. So all of these groups, notice a lot of them have carbonyls. Here we have a cyano group. So this is a carbon triply bonded to a nitrogen. Same type of effect. Nitrogen's more electronegative, so it's going to pull electron density away from that carbon, making it a partially positive carbon. The next thing to know is that Diels Alder reactions are stereospecific. What I mean by this is that if you start with an E or a Z dienophile, the stereochemistry of that dienophile is retained. So if your X groups on your dienophile are cis to each other in the starting material, there will also be cis to each other in the product. If they are trans to each other, then they will be trans to each other in the product. In addition, an alkyne can also function as a dienophile. So in this case, if we move our pi bonds around, notice we still have one pi bond on the right side from the dienophile because you're just going to lose one of the two pi bonds here in forming the ring. Here is an animation of the Diels Alder. So your diene is on the right hand side. Your dienophile is on the left. They're going to come together. And notice the A groups in green are cis to each other in the dienophile. And now your two sigma bonds form. And the A groups are still cis in the adduct. So on this screen, you see a variety of Diels Alder reactions. They all start with the same diene, butadiene, shown on the left, but they all are reacting with a different dienophile shown on the right. So choose any of these reactions and draw the product on a piece of paper. Take a picture of what you drew and then paste that into the chat. Here we have a slightly different question. You're given the products, and I want you to figure out what are the two reactants that you would react together to get this product. So you're going to need to break bonds and think retrosynthetically. So think in a backwards direction. What diene and dienophile could be used to create these products shown? Recall that dienes can exist in an S-cis or an S-trans conformation because there's free rotation around that single sigma bond. However, the Diels Alder reaction can only occur if the diene is in the S-cis conformation. So if we look at this compound, notice that that diene is locked in the S-trans conformation. Therefore, if you try to do a Diels Alder reaction with it, it will not work. And that's because these carbons are too far apart and can't adopt the proper orientation for that cyclic transition state. Conversely, dienes that are locked into the S-cis conformation, such as cyclopentadiene, they're locked in a ring, undergo Diels Alder reactions readily. Now in this case, if you start with a cyclic diene, notice what happens to that carbon. It gets pushed up and you have what's called a bridged product. And then one further nuance is that if you're making bicyclic products, there are terms endo and exo that are used to describe the positioning of these groups in the product. We can consider this to be a bridged bicyclic system. This bridge has one carbon atom and this bridge has two. If the group on the dienophile is closer to the larger bridge, we call it endo. If it's anti to the larger bridge, we call it exo. Typically, we get the endo product as the major product and the exo product as the minor product. The reason for this has to do with favorable orbital interactions in the transition state. If you have a diene and a dienophile reacting such that the electron withdrawing group is tucked under the diene, it can actually interact with the developing pi bond, and that is favorable, and that leads to the endo product. But if you try to orient it the other way, as shown here, that interaction called secondary orbital interactions can occur, and it's not as stable. So here we have a variety of Diels Alder reactions. The diene is on the left, the dienophile is on the right. Choose any of these, draw the product on a piece of paper, take a picture of that and paste it into the chat. Notice all of the dienes are in rings. So therefore these will all form those bridged Diels Alder products. And you will want to make sure that if there is an endo product, that you draw the endo product. I briefly mentioned the molecular orbitals for dienes, and here we have an example of butadiene and ethylene, the simplest combination of reactants to do a Diels Alder reaction. So here we have the HOMO of the diene, and we see here the LUMO, lowest unoccupied molecular orbital of ethylene. In a Diels Alder reaction, if we want to explain it through molecular orbital theory, we would say, well, the HOMO of one compound must interact with the LUMO of the other. So the LUMO is unoccupied, so we're going to have electrons being moved from the HOMO of one to the LUMO of another. With an electron withdrawing group, the dienophile's LUMO will accept electrons from the diene's HOMO. So here we're going to have electrons move into the LUMO from butadiene to the dienophile. In addition to the Diels Alder, which is a 4+2 cycloaddition, you can also do 2+2 cycloadditions to form, for example, cyclobutane. So it's 2+2 because we have 2 carbons in each reactant participating in the transition state. So we would move 1 pi bond here to form a sigma bond and 1 pi bond there to form a sigma bond. So those are your 2 new sigma bonds formed. Electrocyclic reactions involve conjugated polyenes which undergo cyclization. So in this case, we're going to have 1 pi bond removed and 1 new sigma bond formed. And this pi bond forms the new sigma bond, and these pi bonds simply move over, and you get this cyclic product. You can also do this with butadiene to form this cyclic cyclobutene. And the overall transformation is that we're converting one of the pi bonds into a sigma bond. In sigmatropic rearrangements, this is another type of pericyclic reaction. One sigma bond is simply replaced with the other. So here this pi bond moves to become a sigma bond, this pi bond moves over, and this sigma bond breaks to form a pi bond. So there's no net gain or loss in pi bonds or sigma bonds, it's just their placement is changed, hence it's called a rearrangement. There are different named sigmatropic reactions. A common one is the Cope rearrangement, in which all 6 atoms in the cyclic transition state are carbon atoms, and equilibrium favors the more substituted alkene. So here we have 2 monosubstituted alkenes, but here we have a monosubstituted and a disubstituted. So this particular reaction is going to favor the products. We also have a Claisen rearrangement, which is another type of sigmatropic reaction, and this is the oxygen analog of the Cope rearrangement. And this occurs with allylic vinyl ethers. So here's an ether. An ether is an oxygen with carbons on either side. On one side you have a vinyl group, an alkene. On the other side you have an allyl group. So an allyl group is a double bond with a carbon adjacent to it. And in this, you're going to, again, just simply rearrange. This pi bond forms a new sigma bond, this pi bond moves over, and this sigma bond breaks, creating a new pi bond. So in this, you actually get the aldehyde as your product. An equilibrium here favors the formation of that carbonyl because it's stronger and more thermodynamically stable than a carbon-carbon double bond. Now test your knowledge. What is the major product of the following reaction? So this is going to be a Diels Alder reaction. So this is your diene partner, and this is your dienophile. So in the chat, tell me which product you think would arise from this. Here we have another Diels Alder. So here you have a diene. Notice it's a cyclic diene. The two double bonds are in a ring, and then here's your dienophile. So with the Diels Alder, what product would you get? A, B, C, or D? Let me know in the chat. So on this screen, you see a variety of Diels Alder reactions. They all start with the same diene, butadiene, shown on the left, but they all are reacting with a different dienophile, shown on the right. So choose any of these reactions and draw the product on a piece of paper. Take a picture of what you drew and then paste that into the chat.